Okay, well, welcome everyone. There we go. Perfect. Just make sure you got that. All right, well, thanks for coming out. This is the first Friday Astronomy of 2025. We're really excited to have you. Well, welcome everyone. There we go. Perfect. Oh, that's very exciting. Thanks for coming out. First Friday Astronomy of 2025. We're really excited to have you. Well, okay. Okay, let's try that again. Yeah, good. Let's turn this up a little bit. There we go. All right. And hopefully we don't have that. So welcome. We have a great season of talks scheduled for you here in the spring semester. If you've not already grabbed a flyer, be sure to grab a flyer for our upcoming season out on the table. Lots of really great talks coming up, including tonight's. As you all know probably by now, these are donor-supported events. So if you like these monthly astronomy lectures, which happen on the first Friday of every month, 7:30 p.m. If you enjoy these kinds of presentations, please consider donating. We have information about how to donate to the program out on the table there. As I said, these take place on the first Friday of every month, 7:30. We're in this room for this semester. If the weather is clear and it's not too cold outside, the students will do some stargazing out on the plaza or the quad. If you haven't been to the quad, it's where the brightly lit Christmas tree is, grassy area just to the west of here. Tonight, we're not going to do it. You might have noticed it's raining, but maybe next month we'll have good weather and we'll do some stargazing out there. In addition to this programming, I want to point you to another program that's upcoming. The Boise Astronomical Society is hosting their annual I Got a Telescope for Christmas, Now What? Program. This is for folks who have a scope and they're not quite sure how to use it, or maybe you just managed to find a telescope in your closet and you really want to think about using it. They do this program. It's 7 p.m., right, Leaf? 7 at Answer Charter over on 36th. So just a little bit west of here. And they set up the whole gym, and folks basically from all over town bring their telescopes out and then get help with using them. Or if something's broken, they get help fixing it. Highly recommended. It's a really great program, a lot of fun. So join them for that. Okay. And with that, I'd like to welcome our guest speaker for tonight, Professor James Dull, as a professor at College of Idaho. He has a really interesting background, so I'll let him tell you the story of his background. You're not going to tell the story of your background. You're going to leave it unknown. Okay. He's an enigma. But I think he's going to tell you about a very interesting astronomical enigma, which are BE stars. And so with that, let's welcome Professor James Dull. Absolutely.
Is this? Yeah, yes. Okay. They say that you should always start with a joke, right? So I'm going to start with the best one I know. All work and no play makes James dull. Okay. I heard that when I was in third grade. I've never forgotten it. It's absolutely wonderful. So I'll give you a little bit of my background. I am not an observer by training. I went to graduate school. I was a computational astrophysicist, which meant I sat by a computer. I never looked through a telescope. I sat by a computer and I programmed and made things blow up and evolve over billions of years, and that's how I did it. As soon as I finished graduate school, my research became obsolete because they got new computers that were able to replace what I did. So I became an observer, because in Caldwell, what else can you do, right? And so ultimately, I started with that. Now I want to make sure that you notice these images on the first two slides. Both of them are done by a local amateur astronomer, Joe Daglin. The first one I think is pretty obvious. He did both of these in Caldwell using his setup. Pretty amazing images. What we're going to talk about tonight is the following. I'm going to introduce you to our observatory. So the telescope, the spectrometer. So I'll talk about a little bit about the hardware. If you have questions, because I know a lot of you are interested in the hardware and the observatory itself, ask. Stop me in the middle of this talk. I'm really want to answer the questions. I'm not an expert by any means on the theory of BE stars. I am now an observer. Okay, so I can tell you how to use the spectroscope and what the spectra tell you about the star, but I can't tell you necessarily all there is to know about why that happens. All right, then I'm going to introduce BE stars. What are they? H alpha, why is that important? Decretion, which is probably one of the words that you haven't heard before. You've heard of an accretion disk. We're going to talk about a decretion disk. Okay, inclination of observation, what we hope to learn from all of this. And then finally, variability, which is what I've been working on. So the variability of the spectra for these BE stars. And then I'll end with other activities that we're doing out in Caldwell, which is how can we use spectra to look at other stars other than BE stars. So we're going to look at some magnetic stars, in particular hot magnetic stars, and so to see what we can see. All right. Isn't that beautiful? College of Idaho had a dome when I got there in 1998, had a nice dome with a 14-inch celestron in it that was on a German mount that was basically worthless. So over time, we replaced the mount and the tube, and then we automated the observatory. So that means we could control it from the basement or from home if we wanted to be there. It also had a silver, it's an aluminum dome. We found out very quickly that that was hard to use in the summertime. It got up to 120 degrees inside the dome, and we're trying to observe at 11 p.m. And you would think it'd start to cool off, but not inside the dome. So what we did was we got this special paint, and we painted the entire dome by ourselves, mind you. It's really difficult to climb a dome, by the way, because the ladder didn't reach up. So we would hang from the dome, and we painted that thing, and now it doesn't get above 100 degrees in there. So the students are able to work under those conditions. The rule is if it gets above 100 degrees, stop, because I don't want them to hurt themselves. But for the most part, it hasn't been over 100 degrees now for the last 6 years, even though we had a really hot summer last summer. It was 96 was the warmest it got inside the dome. All right, so let's talk about the telescope. We have a 14-inch celestron, new celestron, not the same orange one that we had before. The focal length, you know about this stuff, Paramount mount, so it's an automated mount, which allows us to control it very easily. We cannot look through the telescope. It's all connected up to the computer. So there's no way to actually look through it. It does have an autofocuser on it, which again allows us to control everything. It's run by the SkyX software. I don't know if any of you are familiar with that, but it's a really nice piece of software that allows us to control every piece of equipment as well as map the nighttime sky, and then gives us alarm warnings when we're going to hit the pier. Okay, we've attached L high-res 3 spectrograph on this thing with an R value of 14,000 and 2 cameras, and I'll show you the image of, well, I'll show you the image now. 2 cameras. Let's see. Are you there? So this one goes through the spectrograph. This one is attached to the telescope. So this is basically our spotting scope. So it gives us the field of view when we look for the stars. This one is going to be only focused on the star of interest. This is the spectrometer. And then we have the autofocuser here. And then you can just see the little bit up here is an Arduino that we've attached there that allows us to control some of the aspects that are typically not controllable when we bought the hardware. We had to dial in some things by hand, like taking flat fields. I don't know if any of you are familiar with that, but it's a type of calibration image that you have to take. Well, we've automated that so we can run it from the computer by asking a student who knew how to program to build it for us. That's all you have to do is find a student. If they're 19 years old, they can do this stuff. It's a nice little telescope. Obviously, at 14 inches, it's not going to do a whole lot, okay? Why did we move to spectroscopy? So let's talk a little bit about that. Well, we moved to spectroscopy because initially we did photometry. Photometry is great, except you're looking at a big section of the sky. And in Caldwell, that was fine until about 2008. And then the sky started to get too bright. We could only look southwest. So that means we were only looking toward the Owyhees. So basically, it became less and less usable. About 2015, 2016, we decided that what we would do is we would change to spectroscopy because now it's just a narrow slit. We get rid of all that light pollution. We only have to look at one little star. And that, since then, we built it up and we've been taking images of these bright stars. They usually have to be fairly bright because if you only have a slit of light for the light to come through, that means you can only get part of the light from the star. And so if you're looking at a 10th magnitude star, that's going to take you an hour on each frame that you're going to take. So at 6th magnitude, we spend 10 minutes for each frame, and we take 6 frames. So we get basically an hour's worth of observing over those frames. And that's what we have to do. At 3rd magnitude, we can cut that in half. Okay. It's really nice to do a 1st magnitude star because you just turn it on, 30 seconds later, you're done. You don't have to take any more images. But this is one of the things we play with. One of the things we do have to struggle with this system, however, is, I don't know if you're familiar with a C14 telescope. Essentially, they have a very small field of view when we've attached this on there. So that means we have so few stars in our field of view most of the time that it's hard to use the auto guider. So that's why I hire students to go up there and sit and babysit the telescope to make sure that the slit stays on the star of interest. We could do it with an auto guider, but if we only have 3 stars in the frame, the auto guider is not going to do a very good job. So computers can't do everything. It's basically what it turns out to be. Let's introduce what BE stars are now. So BE stars are B stars that have emission lines. Now I have to sort of unpack that. First of all, a B star is going to be a star. So you look at it, this is an HR diagram. So basically this is the temperature down here in the bottom. And we are simply saying, oh, a B star is in this range right here. So everything in that range vertically is a B star. So about 10,000 to 30,000 Kelvin. Okay. This is going to be the brightness of the star. It says absolute magnitude, but we can just call it the brightness. And so you can see that what happens is these B stars are fairly bright stars on the main sequence or in the giant region here. That's the area we're looking at. The sun, for example, is over here. It's fairly dim. You can see it's a yellow star. It's relatively cool, so it's at about 6,000 K. Right? So that's the B star. What do I mean by the E, the emission? Well, we can have 3 different types of spectra. We're usually interested in 2 of them. One is the absorption spectrum, which is what most typical stars have. An absorption spectrum means that you're going to have a continuum. I don't want to do that. I'll show you a picture of that in a little bit. You'll have a continuum, and then you'll have a big dip where some of the light is absorbed by the surrounding cooler gas, the atmosphere of the star, if you will. For BE stars, rather than having that big dip, what we have is a peak. So we get an emission line occurring in the Balmer series, the hydrogen lines. So at hydrogen, H alpha, the bright line in hydrogen, or H beta, we get a peak rather than the dip. That means light is being produced at that wavelength. The question is, where is that light coming from? Okay. Some of the properties of BE stars, they're rapidly rotating, usually main sequence or giant stars. Presence of a decretion disk, a disk that is created by the star throwing off gas because it's rotating so rapidly. And they have Balmer emission lines, and that's why they're classified as the E for emission. They were originally classified as peculiar stars, and so nobody even looked at them very much, but they changed that classification. So what are the, yes? I'll get to that. Okay. But that's a great question. The questions of interest when we talk about B stars are, do all B stars go through the BE phase? That's an important question. They want to know, is that a normal stage of evolution for a star? And then how does the mass transfer occur? How does the mass go from the star to the disk and stay there? Because remember, you all have that gravitation from the star. It's going to pull that stuff back in unless there's a way to put that angular momentum back out to that disk to keep it there. Now, if I throw a lot of words at you, just nod your head and say, oh, yeah, and smile at me. Seriously, if you have a question, make sure you ask, because I am throwing some words and I don't know what your level of understanding of this material is. Okay. Basically, we've known B stars have existed for about 150 years, but we really didn't get interested in them until the mid-90s. And that's because they found out that, oh, this is a great way to understand the astrophysics of hot stars by looking at these things and trying to understand the dynamic processes that these stars undergo. So I want to give you the formal definition for a BE star. Now bear with me. A non-supergiant B star whose spectrum has or had at some time one or more Balmer lines in emission. Oh my goodness, that is the most arbitrary, no, it's not. It's the most general definition that you could possibly think of. The only thing that's specific here is it's a non-supergiant. Everything else basically is arbitrary. There are so many things so many B stars, types of B stars you can have that might have had emission at some time and don't have emission any longer. So we have to take that into account. Okay. This is a BE star. It is 53 Boo, so the constellation Boise, or it's HD 138629 if you want to get formal about it. That does not look like emission. So let me point this out. Here's the continuum. That's the flat part on either side. By the way, this spectrum was taken from using our telescope in Caldwell. This is just an atmospheric line, right? We have atmospheric absorption lines due to water vapor. And so you have a lot of those types of lines occurring. And then we get this big absorption curve. Now I've taken an image of B53 Boo every year since we set up the telescope. It's never had an emission line. But the definition says it has to have had it at one time. So someone in the past, I don't know when, saw an emission line. This is H alpha, by the way, we can tell by the wavelength. That's the brightest line in hydrogen. So that's created by hydrogen. Does everyone know where the absorption line comes from, by the way? Anyone not know where it comes from? All right. So what happens is we have electrons that are or an electron that's orbiting the hydrogen, the proton in hydrogen. Okay? If there is a photon of a specific wavelength that comes through, the electron will absorb that photon and go to a higher orbit. That's how we think of it. That isn't really what happens, but that's how we think of it. So it's absorbed that energy. That means some of the light, that photon is now gone. So it gets darker. We lose that light at that wavelength. If it's emission, the opposite is going to happen. The electron's at a higher orbit, and it's going to drop down to a lower orbit. When it does so, it's going to give up a photon, some light, and you're going to have light, extra light. So it's going to go the other way. It's going to go up like that. Okay? So this is an absorption curve. And it's a BE star, although it doesn't show any emission right now in any of its lines. Okay. So most main sequence stars look like this when we look at the absorption of the hydrogen H alpha, the hydrogen alpha line. They all look like that. For most, the sun's star, the sun spectrum looks like that, for instance. This is your classic BE star. You see the difference? Again, here's the continuum, and you look at the resolution on this thing. I mean, it's just amazing we were able to get this with our little telescope. So here's the continuum down here, and we get this huge hydrogen line, same wavelength as the last one, only now it's emission. We're getting extra light coming from it, okay? So this is a spectrum of Upsilon Cygni, or Cygnus, it's in Cygnus. It's a classic BE profile. This is what we expect. It looks like a nice peak. We do know that this star does undergo outbursts, so there's some variability in this star. And the H alpha, this intensity, this peak, either increases or decreases depending upon the cycle that it happens to be in. That's what I'm interested in, is where does this variability come from? Yes?
What's the time frame to produce a graph like that?
It's a stack of 6 10-minute images. So my students will spend an hour taking the observations. They'll spend an hour setting the telescope up, because you have to get everything cooled down properly. They'll then take the images, which is the easy part, and then they move on. So in the summer night, we get 5 hours, in the middle of summer, we get 5 hours of usable darkness. So we can get 3 stars in. Okay, and then they have to reduce the images. I'd be happy to talk about the reduction process. By that, I mean we have to calibrate everything. We have to make sure the wavelength is calibrated. We have to make sure that we've taken into account any extraneous noise, electronic noise that might be there, any light that might be coming from external sources. And so we have to account for the variability of the pixels of the camera. And they spend more time probably reducing the images than they do actually taking the images. So they'll spend 2 or 3 hours on each set of images to produce something that looks like this. And then after we're done with these, we submit them to an international database. It's called BESS, the BE Star database. It's located in France, and then they will either accept it, so they go through it and they vet it to see if it has the right calibration, to look at the wavelengths. Again, you see these little absorption lines. They use these to help them vet on whether the calibration process has been done properly. And then they'll accept it or not. And then once it's accepted, it sits on this database. We have put images up there. They have been used by other astronomers who have done publications. So we've gotten images from two of our images, sets of images, have been used in publications. That's pretty interesting to say that with only a 14-inch telescope in Caldwell, Idaho, that's run on basically a shoestring budget. It's pretty impressive. Our students like that. They like to see their names on papers. Okay. Oh, BE stars. And this now is starting to get interesting. That other one, remember, was the classic BE star. Look what we have here. We have 2 peaks. Here's the continuum. Again, here's the atmospheric line that we're talking about, the continuum. We have another one where we have the continuum, atmospheric line. We have a peak, but this one's much lower than that one, with the central absorption peak being deeper. And then we have a third one, which, there's the emission profile. So we have two emission peaks, and then one huge absorption peak that goes below the continuum. These are all BE stars. Let's look at the left one. It's a double peak profile with the decreasing H alpha. So for this particular star, what is it? It doesn't have just a catalog number. It's a main sequence star, so it's a B5 star. So it's a middle range of the B stars. Basically, the red side, or excuse me, the blue side and the red side are almost the same height, so intensity, if you will. And there's some variability in the star that we see, but for the most part, that's what it always looks like. It changes a little bit. If we look at this next one, we have to be careful. This is called the Chiliac, or it also has an HD number. It's been classified as a classical BE star. However, what it is, it's a close binary system consisting of 2 B-type stars. So it's actually not a BE star at all. It doesn't have a decretion disk, but it has almost identical profile. This is what I mean. The definition is so general that we have to be careful. It's been classified as a BE star, but it turns out it's not. Okay. Then we get to this one, which is my favorite. This huge absorption profile in a star in Andromeda It's a giant star. It has a couple of properties. It too is a binary star system, but it is a BE star, but it has this prominent absorption profile that is occurring because of how we look at it, how we see it. This system is actually not a binary system, it's a 4-star system. So it's very, very complicated. But again, the absorption profile and just this, they call this a shell BE star because whenever that absorption profile is below the continuum, they refer to it as a shell. That gives you a clue as to what's happening, how we classify these things. So let's look at that. I don't want anyone to fall asleep, so if you need me to, I can yell. Okay. So what happens is, this is our model for the BE star. So we have the star that's rotating rapidly. You see that it's not spherical. It doesn't look like a circle. It's sort of been compressed like the Earth is because of its rotation. So it's more like an oblate spheroid. It's surrounded by this circumstellar gas and dust that's been thrown off from the surface of the star because of the rapid rotation. That dust gets pushed out along this, the equatorial region of the star. The spin axis is this axis up here. And so it's the dust and gas is thinner up here and much thicker there. So if I'm looking at this star system from this point of view up here from the polar region, I'm going to get something that looks like that, a classical BE star. If I'm looking at somewhere, let's say C, so I'm looking through all of this gas and dust before I get here, that means I'm going to get some emission, but I'm also going to get absorption because of all that gas and dust in that disk. And so I'm going to get something that looks like that shell star. That's why it's called a shell star. We have that shell of gas and dust. Okay. If I'm looking somewhere in between, I get something in between. You'll notice that I get a separation of peaks here. I don't have a separation of peaks here. Why is that? Anyone want to take a guess? I feel like I should teach a class now. Anyone want to take a guess on why I'm getting 2 peaks here and here, but only 1 there? Pardon me? It's spinning, but what does that do? We get something called the Doppler effect, right? One side is coming toward us, and one side is moving away from us. So I'm going to get this single peak separated into a violet peak or a blue peak and a red peak. The red is moving away, red shifted. The blue is blue shifted toward us. So that is a more prominent, I move down toward the equatorial region, I'm going to get this wider separation that occurs. That's how we know something about the rate at which it's spinning. And this is just the disk, mind you. All of these features are coming from the disk, not the star itself. Okay. The problem with this is we want to know how big the region is that's causing these features. We want to know how fast they're moving, which we can sort of figure out. And we want to know how were they produced. In other words, what created this? Well, if these are hot regions, which you need for emission lines, hot hydrogen gas, if they're hot regions, then mostly what we can say is something about the size of the hot hydrogen region, but not the size of the disk itself. Does that make sense? So we have a whole disk, only part of it has a hot region, a little hot spot in it, and that's the part that's emitting the hydrogen. And as it rapidly rotates, we get the splitting of lines depending on our point of view, and we can say how big that region is and how fast that region is moving, but we can't say anything else about the disk directly. So there's a lot of physics going on in this, and it's kind of fun to think about. All right. Yes? Yes. We can only see a star at one angle, right? Each star is going to have a different angle. Some stars are going to be edge on, so the equatorial region is right along our line of sight. Other stars, we're going to look down from the pole, and they don't change relative to us because all the stars are going to be tilted slightly differently relative to our line of sight. And so this star will always have something that looks like this. Okay? But if I look at another star that has exactly the same properties but is tilted at a different angle, it will look different. it may look like this. Yes,
Do you have enough of those visualizations to show a pattern?
a pattern of, you mean based on the angles?
Yeah.
I have not put that together, but that's a great idea. I've never thought about that. Okay, he'll do that. Okay. I'll just send a bunch of images. Okay, let's go on. How do we learn about the star's rotation? So now I'm going to introduce some equations here. That's okay. So I'm going to introduce this angle I, which is the angle of the pole of the star relative to the line of sight to Earth. So that's the inclination angle, if you will. There's going to be an equatorial velocity here. So the star's spinning, right? So it's like the Earth has a certain rate of spin as measured from the equator. So we're going to take that projection of the equatorial velocity of the star and project it down onto our line of sight, and we get V sine I. That's what we can measure by looking at the spectrum of a star. It'll be shifted either right or left. Okay? We can measure that, so that gives us a minimum velocity for that star. All right? So that's how we're going to find out the velocity. It's kind of fun to play with this. Now, these stars rotate fast enough so that many of them are near the critical value. Does everyone know what I mean by critical value? You could say no. Critical value means you're at the point where you're starting to, imagine you're on a merry-go-round and someone pushes it hard enough that you start to fall off and you're hanging on only by your hands. At some point, you're going to have to let go. That's the critical value. Okay? So the star is spinning like that and mass is being thrown off. The littler kids are being tossed off the merry-go-round, if you will. And they're going to be thrown out there, and just like any disk, any mass that's thrown off a spinning object is going to ultimately form into a disk because it still has that angular momentum. It still has to spin, right? So we've all seen how pizza, if you spin the pizza dough, it gets flatter and flatter. That's what's happening here. That's what's called a decretion disk. Decretion, it's made from the star. The star is not gathering the mass like an accretion disk. It's throwing mass off. And that's because of the rapid rotation. However, it is not at its critical value, its critical speed of rotation speed. So that means there must be another mechanism that's helping toss that mass out there. Okay? Because it's below the critical value, it's not going to tear itself apart. That means if it starts to throw that mass off, there must be something contributing to that. And as that mass gets out there further and further away, we know about what happens, right? The ice skater effect. Fast if your arms are in, slow if your arms are out. As that mass gets out there further and further, it's going to spin slower and slower. But that means if it spins slower and slower, it will be attracted back to the star again. Okay, but it's not. Yes. No. But there, yes, it's dark something. When astronomers don't know, they say dark something, right? Dark energy, dark matter. Yeah. No, we don't know what the mechanism is, but it has to be there. Something has to be contributing the angular momentum of that disk to keep it as a disk rather than allowing it to fall back into the star. Yes.
You mentioned how many of these are binary?
Well, about 60% of all stars in our galaxy are binary, so we assume it's the same fraction. Okay. The global waves may exist. Has anyone heard of a density wave for the Milky Way? These waves it's called a mass density wave. So it's a wave that goes through the disk of the Milky Way, and it creates a pocket where the stars get closer together, so they're more dense, and then a pocket where they're less dense. That's what creates the arms of a spiral galaxy. A similar thing is happening in this disk that we believe accounts for the variability of the disk of these stars. So it's a very slow-moving density wave, one-arm density wave, that basically keeps scrunching the mass together and then allowing it to dissipate as the wave moves through this disk. That may be contributing to that angular momentum, but it definitely contributes to the variability of these stars. Because obviously, if you get a higher dense higher density region in the disk, that means you're going to have more opportunity for interactions and you can have more emission. So lots more emission, brighter. As the density wave goes through, less emission, dimmer. And so we get variability of the brightness in the spectrum. Okay. Questions? More terms. I need all of these because they make me happy. The spectral properties. What are we going to do? How are we going to look at these and define all of these weird BE stars? We have so many different shapes. How are we going to compare one to the other? And so we use these different values, all spectral properties. Equivalent width. Equivalent width, if this is my spectral line, the red line here, how wide would a rectangle have to be to have the same area? That's the equivalent width. That's all it is. Okay? VR. Did I hear a question? VR. Violet red, the relative strength of the two peaks. When I have two peaks, how are they? Are they equal? Is one higher than the other? Is one lower than the other? Okay. EC, which is the emission peak max over the continuum value. All of these are basically trying to measure something similar, which is the total amount of energy associated with that line profile. And then the last one, which if anyone's done any statistics, we recognize this as full width half max. So you look what is the width of this thing at half its maximum of half the red line there. Okay? These are all ways in which we can try to estimate the energy. Limitations, and I've talked about this already, only the emitting regions have these characteristics. So what we're really doing is defining the emitting regions of the disk. We can't talk about the entire disk. Let's see. Let me scroll down here. I want to make sure that I cover all this because it might be important later on. Many of these features, by the way, are related to that V sin I that I've already talked about, this rate at which the star is rotating. So we have a lot of complicating factors here. And that's why so many observations need to be done. How many people are amateur astronomers in here, are actually doing, this is something that you can contribute to. It really only takes a little while to learn, although the hardware can be expensive initially. It's something that you can do easily in your backyard. Okay. So what we're looking at now, I've replaced the fake image with a real image here. So now if we look at the VR ratio, you can see that the violet end here and the red end here, obviously if I take that ratio of those two peak values, I'm going to get something less than 1. Or yes, something less than 1 in that case. If I take EC, I'm going to take the maximum value and measure it relative to the continuum. Now we've set up all of our spectrum so the continuum is always placed at a value of 1. You can place it at 0 if you want to, but we always set it at 1. And so you can see that this is about a 2.5-ish for that peak. The EC, the peak height above the continuum, and then the full width half maximum, we don't. It's really hard to get a full width half max for a double peak system like this. If I have a classic BE star system, it's a little bit easier. Okay. Now that we have all the terms defined, we can start to look at what I'm really interested in is the variability. So this is Kappa Draconis. I've looked at the star a lot. First of all, the bottom star here is Arcturus. Classic absorption profile. So that's what we expect from a normal star. Remember all of these lines here, these little absorption lines are from our atmosphere. So now we look at Kappa Dra, and I took this over, I think there are 6 or 7 different images, 6 or 7 different nights in here. And I've tried to put them all together. Again, you see that these lines, the atmospheric lines, are all in the same place. So that's good. But you see, look at the variability in these stars. So if I look at the green here here's the violet end of the peak, and then the red end of the peak. But if I look at the bright blue here, now here's the violet and the red. So we can see that it's flip-flopping. So we see there's a big variation in what's happening with the VR ratio. See, one thing I think I want to talk about, oh yeah. Arcturus, by the way, is used as a standard spectroscopic star. That's why it was included in this image. So we always compare our spectra to standard spectroscopic stars because we know exactly what Arcturus should look like based on everyone else's measurements of Arcturus. All right. Now you'll know that there are, if you look closely here, the green again, there's the violet, there's the red. Oh, there's a third peak in there. Well, that's kind of weird. We haven't talked about 3 peaks. If I look at that day up close all by itself, all of a sudden I get another emission peak. Where's that emission line coming from? Well, it turns out that there may be some other hotspot occurring because of the interaction between the star's modulation, if you will. This is a binary system, and the disk. So because of the variation of the 2 stars orbiting each other, we have that disk in there. That modulation of the orbits of the 2 stars is creating another sort of a squeezing effect in the disk that's creating another hotspot at some time in the orbit around each other. And so this obviously complicates how we're going to model this star. You'll notice it didn't happen. Let me go back one. It doesn't happen all the time. We only really see that central peak on one day. If I stack the images rather than put them all on top of one another, so I have what, 9 images from 5th of June to the 25th of July in 2019. So down here, you can see that we have almost equal brightness in the peaks. Now the violet is brighter, and then you can't really see the third peak in here, but now it's flip-flopped again. So now the red end is brighter. When you stack them like this, you can't put as much detail into the image as you want to. But if I look at the data, I'm going to look at equivalent width here. So remember, equivalent width is a measure of the equivalent area, and you're going, why is there a minus sign? Astronomy. Okay. If it's emission, it's negative. If it's absorption, it's positive. Astronomers, if it's bright star, it has a low number. If it's a dim star, it has a high number. Everything's opposite in astronomy. So look at these numbers. Look at the equivalent width. Remember, this is a measure of the energy of the star, of that particular line. So we have a minus 607, and you can see that it continually gets smaller, a little bit bigger, small. So there's definitely something going on here. And it happens that this is definitely connected to the orbit of the 2 stars about one another. Okay. So what we get is that if you look at this over my 5-year period that I've been observing this star, you find out that this equivalent width is actually at a 30-year minimum right now. That's kind of cool because if we keep observing, maybe it'll become much, much brighter, and we'll be able to say something about the dynamics of that system by looking at the periodicity of the variability. Okay. Let's see. Let's move on to a different star. That one's boring. Actually, it's not. Let's move on to CX Draconis. What's the first thing you do when you look at this one? What's the first thing you notice? Okay. First thing I notice is, wait a second. If I go down here, my continuum's at 1, but my peaks are just a little tiny bit above 1. It's a much dimmer star. It's much, much dimmer than the last star system we looked at. And so we can see that basically we get this absorption line. So this is a shell. It's in a shell phase here. Now it's no longer in a shell phase. We get and the violet peak is bigger than the red peak. Now we get red peak bigger than violet. Same, all it disappears. That's kind of weird. and then they're equal again, and it starts to get red bigger than violet. So lots of variation going on here. What's happening here is that we have a star system with basically it's a contact binary. And they have a period of 6.7 days. And the periodicity of this thing, if we were to look, is going to be 6.7 days. That variation. And it's a true periodicity, not like Capidraw had a periodicity of 23 years in its profile, but it wasn't a real period because it didn't have the same shape each time. This one has the same shape. And this, when it disappears completely, happens to be when we get that exact line of sight interaction between the two stars. And it's really kind of exciting to think about. If we look at the equivalent width, so we see immediately we get a positive value here. All the rest are negative. So we're getting a real cool variation here. This delta V, by the way, is just the change in velocity of one side relative to the other. It's not a big deal. Okay. Questions on this? This is what I'm looking at. My hope is that I'll be able to look at these systems using the observatory in Caldwell over the next couple of years. Continue to get the spectrum. So my students will be, when I say my students will be up there every night observing during the summer. They don't observe during the winter because weather. And I'll be at Bruno, I hope, taking photometry of the same star systems. So I'll be able to look at the variability in the brightness of those star systems as well as in their spectra. Yes?
So when you see these wobbles between the violet side and the red side when the peaks trade off, what is actually happening there? Is that the angle at which we're seeing the binary star system? Or is that
In this particular case, it probably has something to do with the binary star system. In other cases, it may simply be a change in the size of the emitting region. So, I mean, if something is bigger, it's going to be brighter. And if it's bigger on the side that's going away from us, it's going to be brighter on the red side. If it's bigger on the other side, the side coming toward us, it's going to be brighter on the blue side. Yes?
Binaries, the partner is kind of caught in the accretion disk of the RE.
Yeah, they're sharing mass in this particular case. This is, when I say it's a contact binary, basically the surfaces of the stars are nearly touching. I mean, if you think about it, it has a period, two stars, they're going about each other every 6 days. They have to be very close together, right? Mercury takes 88 days to go around the sun. So these stars have to be much closer than Mercury is to the sun. Well, no, that's not. Have to, equivalent ratio values. You have to take into account the fact that the stars are huge. Yes, was there someone else raised their hand? Pardon me? Okay, because the emission lines only occur in hydrogen, sometimes helium, and sometimes iron. We could, but it's not guaranteed. Remember, the definition of a star is hydrogen emission for a BE star. So we know that there's going to be H alpha, and H alpha is a bright, bright line, so it's easy to see. If we look at a helium line, it won't be as big. And so it's harder to get all the measurements we want. Yes?
So just see if I understand what's going on with the decretion disk, is that in these stars, you're seeing, there's this disk around it and it's flinging out matter, but not at the critical value. So there's something else that's causing it to fling out matter. And then that matter is going out far enough that it's not completely getting flung out, but it still flows by, where now it just slows down, goes to the outer rim of the disk, and then just eventually gets sucked back in.
It doesn't get sucked back in. It stays out there at the disk. The disk may dissipate over time. In fact, it probably does. The key thing is that only about 15% of the stars, the B stars we observe, are actually BE stars, or have a BE phase. We don't know if all B stars go through a BE phase, but right now they don't believe that's true. They believe that this is a special phase for the ones that are most rapidly rotating or have a special mechanism in which we can keep pumping the angular momentum out to that disk to maintain the disk.
So
Yes. That we know. There are other things that have disks. Obviously, protoplanetary nebulae. Anything that's spinning, has some kind of gas or dust around it is going to have a disk. Galaxies have disks. So the disk dynamics, the equations that govern that disk, are the same for all those disks. Decretion disks are only weird in that they're produced the opposite way. They're not accreting toward the center like most disks do. They are actually decreting from the center. Okay. Now, there's one last thing that I want to mention before I finish. Is we don't only look at BE stars. We have fun with other things. There's something called the Zeeman effect. Okay. The Zeeman effect is an effect on spectral lines that occurs in high magnetic fields. So in the laboratory, we can take any spectral line, well, not any, most spectral lines, and we can cause the spectral line to split into multiple pieces. There it is. So here is what the silicon line, this is ionized silicon, will look like, where there's no Zeeman effect. Here is where we get a splitting of the lines caused by the magnetic field. How much it splits depends upon the strength of the magnetic field. So what we did was we looked at an AP star. That's a class A star, which is a little cooler, or a lot cooler, than a B star. But the P stands for peculiar, because it shows the Zeeman effect. It has some kind of peculiar feature in its spectrum. So this is not hydrogen, this is silicon, ionized silicon. And we get two lines here. And if we measure the separation of these two peaks, we can find out what the total magnetic field is for that star. We can approximate it. There's this equation that allows us to determine that magnetic field. So I had some students do this for that particular star. And you take into account some quantum mechanics. There's something called the G factor that you have to take into account. It tells us how probable something is. The light came on and reflected off my glasses. It tells you how probable the splitting is for that particular line. And we did it not only for silicon, we did it for an iron line, and we did it for a calcium line. But what we found out for this particular star is we got a value of about 31.5 kilogauss, which is simply a measurement of magnetic field strength for the entire star, which is huge, by the way. That's a really strong magnetic field. The value that is given in the literature is about 34 kilogauss. Again, that's pretty good for a 14-inch telescope in Caldwell. Okay. When we compared it to the other lines, all of them are around 30. So we looked at other features, all of them are around 30 kilogauss for this particular star. Now, why did we choose this particular star? Because it has the biggest magnetic field that we know of that's bright enough for us to observe. And we knew the Zeeman effect would be there. Okay. And it's something that's simple. You can take a picture, obviously 6 pictures, you stack them together, you measure the wavelength here and the wavelength there, take the difference, and then you plug it into the equation to find the magnetic field. That's all there is to this, along with all the science that goes with it. Okay. The students have to do the science, though. I don't have to think about it. Yes?
Are the students doing a lot of this research basically just to learn, or are they doing some of the research and is it furthering something, other research that's going on in other disciplines?
This is contributing to our understanding of the evolution of massive stars, particularly BE stars, and disk astrophysics. It turns out that B stars, these BE stars, happen to be the perfect laboratory for understanding astrophysics of hot stars. We've been ignoring them, but there's much easier to look at a BE star because of all the information that's contained in the spectrum rather than a normal B star to get the same information out of it. Are they contributing? They're getting publications out of it. They do posters. They get paid to work in the summertime. So this is their opportunity to do real research. They're not just sitting at a telescope, by the way, and taking pictures. That's not what they do, okay? Well, it's part of what they do. There is grunt work associated with it, but a lot of it is, how do you interpret what you're doing? How do you know what you're doing is important? What can you find, discover from what you have done? Those are the things that we're asking our students to do. All of them will put it on their resume when they apply to graduate school. Several of them have gotten jobs at places that do data analysis. So for businesses, computer science, because you have to write a computer program to do most of this. So many of them have gotten jobs in business-oriented companies because they can handle large sets of data. I'll end my presentation there and ask if there are any questions. Yes.
Toward the beginning of your talk, you had a diagram that I'm sure is quite simplified. It showed this obloid spheroid and then the envelope of the disk. And it was a lovely diagram that suggests that the disk is quite uniform, like the rings of Saturn. But because of your talk, I'm getting the impression that these disks are more likely to have arms, like the spiral arm.
One arm.
Yeah.
They'll have one arm. An arm. One density wave will be passing through. Yeah, a single arm.
Anybody imaged a radio telescope or anything with a high resolving power?
No, all of this is done using spectra and photometry. Maybe polarimetry will help, so you'll be able to get something with how the magnetic field is changing with these stars, even though they don't have large magnetic fields. But imaging a star, even a bright star like a B star, is difficult to do. We've only really imaged 1 or 2 stars directly, right? With the Webb telescope, I don't know how many more we're going to image, but it's probably not high on their list. They're looking for dark things. Dark things.
The radio telescope.
Radio telescopes don't have the resolution to actually image a star. If you've ever looked at a radio image of a star or a star system, it's very pixelated. It looks like a computer game from the late 80s or early 90s. You know, the animation is very pixelated. And so that's because the resolution on radio telescopes is not very good. Yes.
The slide that has the formula, that one, so the axis on there, I'm curious, in the binary system, those 2 stars rotate so closely together, do they affect the axis of one another that would cause different readings?
Well, usually when 2 objects are rotating around each other, they're going to be rotating around each other's center of mass. So can you have a tilt of the object so it's spinning like this while it's also orbiting in a different plane? Yes. Because that's what the Earth does around the sun, right? We're tilted 23.5 degrees relative to the ecliptic plane. So the plane of the Sun-Earth system. So you can have that tilt. Will it affect it? I'm going to answer that with a definitive, I don't know. Okay, I haven't thought about that, but it's a good question. Any other questions? Yes.
What is the rate of rotation? You keep saying it's high.
Yes, and I do have that number someplace.
Pick it up.
I don't have it off the top of my head, but it's definitely on the higher end. What is the sun's rate of rotation? I'm looking at you two back there. I don't have the number off the top of my head. Yeah.
Relative to the sun.
It's
Yes.
yeah, it's fast. It can't be 100 times faster because a B star is much bigger. So that means gravitationally, the outer layers of that star are much further away from the core. And so they're going to be easier to peel off. So the bigger the object is, the easier to throw off its outer layers. So for instance, you could never reach a spin rate where you could throw off your outer layers because you're just not big enough. Okay, but if you got bigger, you might be able to hit that rate. Yeah, hopefully that never happens. Yeah.
How much does this spectrograph cost?
The one we got cost $6,000. Not a lot of money when you think about what we're able to do with that. The telescope, the tube, cost $10,000. So that's just the tube. The spectrograph and the autofocuser together cost $7,500. The mount costs about $6,000 to $7,000. These are all prices when we bought them, so that's 7 years ago. I don't know what they are now. The automation is probably another $15,000, but you don't need to automate if you're going to be in the observatory. The computer, whatever computers are. So the entire cost is going to be around $20,000 to $30,000 to put a system like this together without automation. If you add the automation so the dome is synced with the telescope and you can control it from indoors or outdoors or from Hawaii if you want to do that, then you're going to add another at least $20,000 to the system. Over time, we've probably spent about $100,000 on the total upgrade to our equipment and the student fees, the student money that we give the students, so the wages.
What's the advantage to observing simultaneously for Caldwell and Bruno?
Well, one's spectroscopes. We're using a spectroscope in Caldwell, we're using photometry in Bruno, well, imaging in Bruno, so we can look at the light variability of the entire system and compare that to the variability associated with the H-alpha line. Any other questions? All right, thank you.
All right, well, thanks for joining us tonight, everyone. Please join us again February 7th for our February event. It should be really great. We've got Dr. Christopher Moore here from Harvard, actually. He's going to talk about small sats. Have a good weekend. We'll see you in February.